Hey, this is Steve Desjardins again, and we're going to talk about formula and names in chemistry. Chemistry, in many ways, is known for its formula and its names. It's one of its iconic features. Long chemical names, long chemical formulas. And this makes sense because we have many, many things to keep track of. The American Chemical Society keeps track of over 150 million different compounds. So you can imagine giving these things unique names is quite an endeavor. One interesting point here, however, is that to really name and understand formulas, you have to understand the answer to the following question. Okay? At the atomic level, so in other words, you shrink down like Ant-Man into the quantum realm. So suddenly you are the size of an atom or a molecule. What particles do you see? And what I mean by this is, what independent particles do you see? I see this thing, I see this thing, and I see this thing. They're not attached to each other, and they float around independently. Now, to understand how this works, okay, we're going to talk about a few basics here. First of all, there are atoms. Atoms have a single nuclei and exactly enough electrons to balance out the positive charge of the nucleus. A good example of a free atom is argon. Argon atoms float around by themselves in argon gas, and they're not attached to anything else. If you were the size of an atom, you would see these large spherical argon atoms floating around. The next possibility is a molecule. Okay? And molecules are collections of atoms, or if you will, things that have more than one nuclei and have enough electrons to balance all the sum of all the positive charges in the molecular nuclei. Okay? And an example of this would be, obviously, water. Okay? So if you were, again, atomic sized, you would see water molecules floating around, two hydrogens attached to an oxygen. They would be the basic kind of free particle floating about. Now, another major class of possibilities is ions. Ions are like atoms and molecules, except they have charges. In other words, the number of electrons does not perfectly counterbalance the positive charges of the nuclei. And it's important to realize that since the nuclei identify the element, the only way to change the charges on an atom or molecule are to either gain or lose electrons. Okay, so they are literally atoms and molecules that have gained or lost electrons. So let's look at some examples. If you have an atom that has gained or lost electrons, you have a monatomic ion, okay, which literally means one atom. Examples of this are chlorine and sodium. Now we note here that ions can be either positively or negatively charged. If you're negatively charged, you're called an anion. If you're positively charged, you're called a cation. The other possibility is that you could literally be a molecule that has gained or lost electrons. Okay? Then you're what we call a polyatomic ion. Examples of this are nitrate, NO3-, and ammonium, NH4+. Now notice what we're saying here, what happens at the atomic level. So for example, if you were in the compound sodium chloride, the basic particles you would see would not be NaCl molecules. They would be chloride ions and sodium ions, not attached to each other, just in combination. So a collection of chloride ions and a collection of sodium ions. Similarly here, okay, if you were to form the compound ammonium nitrate, you would see ammonium ions and you would see nitrate ions. Now, let's think about a little more about molecular formulas. Now, if we're looking at what are called molecular compounds, okay, and a compound is a pure substance that consists of one type of material. Now, it doesn't mean it's elemental, so it's not just oxygen. So again, for example, you could have a compound would be ammonium nitrate, okay, and that would, all there is in the bottle would be ammonium nitrate. Now, molecular compounds consist of, not a surprise here, either the rare case where you have a single atom all by itself, so that would be like argon, or things that can have molecules of various kinds. Now remember, molecules can have the same atom, Cl2, or molecules could be more complicated. You could have something like water, all right? Or you could have something organic, which would be even more complicated. Now, the interesting thing about molecular compounds is that you don't always have the same ratio of one element to another. So if you have two elements in a compound, you can have different ratios of those two. So a good example is nitrogen and oxygen. So you can have N2O, you can have NO, you can have NO2, you can have N2O5. Okay? All of these consist of nitrogen and oxygen, but they can have different numbers of each because these are bound tightly to each other. Now, these things are given all sorts of various names. This one could be called, for example, this one right here could be called dinitrogen oxide, but it's also called nitrous oxide. Okay, and this is actually laughing gas. This is the thing you sometimes get at the dentist office. On the other hand, this is simply called nitrogen oxide. Okay, this would be nitrogen dioxide, and this would be dinitrogen pentoxide. You will notice that when naming these compounds, we use Greek prefixes like di and pent, okay? And when you want to know these, go look up these prefixes in your chemistry book and learn them. And after that, it's very easy to set this up. But this is one of those things you just have to learn. Now, an important thing to remember here is that if you're at the atomic level and you look around in a molecular compound, you will see these molecules. So if you are in dinitrogen oxide, nitrous oxide, you would look around and only see N2O molecules. So you'd see two nitrogens and oxygen bound together into a single particle, a molecule, and they would be floating around. And similarly for all the other compounds present here. Now, let me give you a brief example of organic molecules. Okay, so for example, we could have acetic acid. Acetic acid, better known as vinegar. Okay, or actually vinegar is an aqueous solution of acetic acid. And its particular formula could be written as C2H4O2. Now, the problem here is that organic molecules are larger, and there may be different ways to arrange those atoms. Okay, so you could have the same formula for two things that are actually two different compounds. So as an example of this, okay, I could write, using what's called a Lewis structure, that we have an OH attached to a CH2, attached to a carbon that has a hydrogen and a double bonded oxygen. I could also have a CH3 attached to a carbon that had a double bonded oxygen and an OH group. Okay? And it turns out that this particular structure is acetic acid. So sometimes, rather than write the simple elemental ratio like we have up here, you can write, or organic chemist will write, a formula that indicates a little bit of how things are connected. So acetic acid is often written as CH3COOH, and organic chemists would recognize that the COOH group meant this particular structure. Now, you don't have to know a lot of this for general chemistry. Most of this is saved for all the fun you will have in organic. Okay, I'm going to pause here and come back with part 2 of this video where we'll talk about ions.